Assalamualaikum and a very good day. We're from Group 4 and this is our presentation for Thermodynamics 1 part of the integrated project. We're going to introduce ourselves.
Hello, my name is Teo Junha and my student ID is 20,321.
Hello, my name is Maizato Akmal binti Mahat and my student ID is 20,334.
Hello, my name is Kulavartini Sigarvelu and my student ID is 20,353.
And my name is Mohammad Farid Bagan Mugafa with student ID 20,458. So we're going to start with the schematic diagram by Junhao.
Now I'll present the schematic diagram and details of the power plant. The type of cycle ahead is Rankine cycle. We choose water as the working fluid and cooling medium. So this is basically our proposed geothermal power plant. The whole plant contains 5 units of turbine, 5 units of generator, a condenser, a compressor, 76 units of pump, and a heat exchanger system, which consists of a preheater, an evaporator, and a superheater. Other than that, we also include plant auxiliary systems such as compressed air and fire protection system for maintenance and safety purposes. Next, these are the few assumptions that we made for the calculation part.
So we're going to proceed with the calculations. First part is the compressor, which pumps the geothermal steam to superheater and it increases the pressure of the geothermal steam, and this process is isothermal. For stream A, as mentioned before, the mass flow rate of the geothermal steam is 300 kg per second, and we assume that it is obtained at 800 degrees Celsius and 3 megapascal. The temperature exceeds the critical temperature, and it is found that the state is superheated vapor, and we use table E6 to find the enthalpy of stream A, which is 4146.9 kilojoule per kilogram. And for stream B, it is isothermal, so the TA equals to TB equals to 800 degrees Celsius. And the pressure for stream B is assumed at 6 megapascal. And again, the state is superheated vapor, and we use table E6 to find the enthalpy of stream B, which is 4133.1 kilojoule per kilogram. And the work in for the compressor is found at 4140 kilowatt. And next is the pump, which will pump the working fluid water to the preheater. As we see before, the mass flow rate of the fluid water is 100 kg per second, and we assume that it exits the condenser at 5.33 kilopascal, 33.84 degrees Celsius, and in the state of saturated liquid. And we use the table A5 to know the enthalpy of stream 6, which is found at 141.84 kilojoule per kilogram. And then it exits the pump at assumed temperature of 55 degrees Celsius and assumed pressure at 10 megapascal. And from table A5, we found that the saturation temperature is bigger than T1. We conclude that it is in the state of compressed liquid, and we use table A4 since it is temperature dependent. H1 is equals to HF equals to 230.26 kilojoule per kilogram, and we calculate the work in pump, and we found that the work in is equals to 8842 kilowatt. And next is the heat exchanger 1 preheater, and the process is isobaric. For stream D and E, it is the stream for geothermal superheated steam. We assume that it enters the preheater at 440 degrees Celsius and 6 megapascal. It is in the state of superheated vapor, so we use table E6, and by linear interpolation, we found that the enthalpy of stream D is 3278.10 kilojoule per kilogram. And for stream E, we assume that the superheated steam, geothermal superheated steam, exits the preheater at 300 degrees Celsius and 6 megapascal, and it is in superheated vapor state. And from table E6, we found that HA equals to 2885.6 kilojoule per kilogram, and we found that the Q out from the superheated steam is equals to 117750 kilowatt. And then the stream 1 entering the heat exchanger at 55 degrees Celsius and 10 megapascal in the state of compressed liquid from the previous work. And by energy balance equation, we found that H2 equals to 1407.8 kilojoule per kilogram. And for stream 2, we do some analysis from table A5 at pressure 10 megapascal. We found that it is in the state of saturated liquid, and T2 is equals to 311 degrees Celsius. And for evaporator, we basically use the same procedure where we found the Q out by the geothermal superheated vapor. We assume the inlet of the superheated vapor of the geothermal into the evaporator, and the outlet stream of the geothermal superheated vapor exit the evaporator. And we found that the Q out equals to 131880 kilowatt, and that from stream 2 from the previous work, H2 equals to 7.8 kJ per kilogram. By using energy balance, we found the enthalpy for stream 3 equals to 2725.5 kJ per kilogram. And we do some analysis for stream 3 also, and we found that it is in the state of saturated vapor at the temperature of 311 degrees Celsius. And also the same procedure is used also for the superheater. We found that the Q out by the geothermal superheated steam is 124620 kilowatt. And from there, we use the energy balance equation to find the H4 equals to 3971.7 kilojoule per kilogram. And then we do some analysis for stream 4. We found that it is superheated vapor state, and from table A6, we do linear interpolation to find the T4 and S4. So T4 is 741.6 degrees Celsius, and entropy for stream 4 is 7.269 kilojoule per kilogram Kelvin. And next is the turbines, which is an isotropic process. First, we need to calculate the total power required for the whole power plant, which is 165.02 megawatt. And then this is the condition of stream 4 from the previous work. And for stream 5, since it is isentropic process, so S4 equal to S5 equal to 7.269 kilojoule per kilogram Kelvin, and we assume that P5 equals to 5.33 kilopascal. And from table F5, we do the appropriate analysis to find the T5, H5, and also the S5. And by linear interpolation, we find that T5 equals to 33.84 and the X equals to 0.86, and thus we find that H5 equals to 2235.01 kilojoule per kilogram. And at the end of this, we find the work out from the turbine equals to 173.669 kilowatt. And lastly, the condenser, which is an isobaric process. From the previous work, we find these conditions for stream 5. And for stream 6, since it's isobaric process, so P5 equal to P6 equals to 5.33 kilopascal, and we assume the state to be saturated liquid, which the working fluid water go through phase change through the condenser. And from table A5, we found that H6 equals to 141.84 kilojoule per kilogram, and we found that the Q out from the condenser is equals to 209,317 kilowatt. And this is the total work required for the whole power plant. And we also calculate the efficiency of the power plant, which comes to 42.94%. And here is the temperature specific entropy diagram with respect to saturation lines.
Next is the discussion. So the proposed power plant consists of a compressor, 3 heat exchangers, 5 turbines connected to a generator, a condenser, and many pumps. Before beginning the calculations for the proposed solution, we made a few assumptions. All devices operate in a steady flow. Therefore, all 4 processes that comprise the Rankine cycle can be analyzed as steady flow processes. The power plant is also assumed to be stationary, so kinetic and potential energy changes can be ignored. Is that there is no leakage in the pipeline between the equipment. This ensures that the mass flow rate is constant throughout the plant. We assume that all of the devices in the cycle are adequately insulated to prevent heat loss to the surrounding. The fifth assumption is that geothermal superheated steam can be produced at 800 degrees Celsius and 3 megapascal. The temperature is obtained from the range provided in the details, whereas the pressure is obtained from an external source. The sixth assumption is that the pipelines throughout the plant are 100% efficient. We assume that the process occurs isothermally in the compressor that pumps geothermal steam to the superheater. This is due to the fact that TA equals to TB when both temperatures in stream A and B are constant. Finally, the total work required for the power plant is calculated by using the formula where we have obtained 160,687 kilowatt as our W net out. The efficiency that we have obtained is 42.94%.
Okay, so for the method of solving, first for the first component is compressor, which pumping the geothermal steam to the superheater. The method we use is we assume that the working fluid is geothermal steam, and it is an isothermal process where the temperature for stream A and B is constant. Next, we assume the temperature and pressure. From the thermodynamic table, we know that stream A is superheated vapor and stream B is superheated vapor. So next, we find the enthalpy for stream A and B from the thermodynamic tables, and last, we determine the W in. The second one is pump, which pumping the working fluid water to the preheater. So the working fluid is water and it is an isentropic process. We assume the temperature, pressure and saturated liquid for stream 6 and we assume the temperature and pressure for stream 1. From thermodynamic table, we know that stream 1 is compressed liquid. So the enthalpy for stream 1 and 6, we find it from the thermodynamic table and lastly we determine the W in. So for the heat exchanger 1, which is the preheater, the working fluid for stream D and E is geothermal superheated steam, and the working fluid for stream 1 and 2 is water. It is an isobaric process where the pressure in stream D and E is constant. We assume the pressure and the temperature. From the thermodynamic table, we know that stream D is superheated vapor and stream E is superheated vapor. So we get the enthalpy from the thermodynamic table. Lastly, we determine the Q out. We also use the same method for the heat exchanger 2, which is the evaporator. For the heat exchanger 3 superheater, we also use the same method as the preheater. So for turbines, we have 5 identical units. We assume that the working fluid for stream 4 and 5 is water. It is an isentropic process. Next, we determine the total power required for the whole geothermal power plant. We assume the pressure for stream 5. Next, we determine the entropy, pressure and enthalpy for stream 5. From the thermodynamic table, we know that stream 5 is saturated liquid vapor mixture. So we determine the quality S and the new enthalpy. Lastly, we determine the W in. For the condenser, the working fluid for stream 5 and 6 is water. It is an isobaric process where the pressure in stream 5 and 6 is constant. We assume the stream 6 is saturated vapor. So the temperature and enthalpy for stream 6, we get it from the thermodynamic table. Lastly, we determine the Q out. For total work and efficiency, we determine the total work required for the whole geothermal power plant, and then lastly, we determine the efficiency for the whole geothermal power plant. So that's all from our group for this thermodynamic. This is all the references that we use.